Hey, welcome. Today I will be talking a little bit about the context rot paper. This is a paper that was recently released by the Chroma team. Chroma team is the team responsible for building the ChromaDB, which is the tool to retrieve information and all the engine behind it. And this paper specifically is claiming that context might still be important to optimize. And then we have a whole field which is context engineering, how you can better structure the context. And to do that, they assessed three different problems. The first one, I'm going to be paying more attention to it because I decided to re-implement it. So I will have a different perspective in the same problem. And then we have other two problems. The first one is specifically the one that I decided to re-implement. It's called needle in a haystack. It's when you have a specific piece of information added in the context and you want to retrieve it. The second problem that they explored in this paper, let me find it here. So this is a problem about the conversation history and how it impacts the final result. In this case specifically, they experimented using a more focused context versus the full context, and turns out that the average score is higher when you apply context engineering for all of these models that they assessed. And the last problem that they tackled in this technical report is they asked the LLM to replicate a text, and the text is multiple repeated words and one unique word in the middle. In this problem specifically, they are not only working with the context size as input to the model, but also the output of the model, how it impacts when you increase or decrease. And turns out that as expected, the performance drops when you have a higher context. And they assess it with all of these models, and most of them we have a significant drop in performance. But I'm just overviewing these two problems. Let's jump into the first. The first one is the needle in a haystack. This is when you add a specific needle in the haystack. The haystack is the whole context. The needle is a piece of information that you have to match. This is the simplest version of it. We have a clear match between both instances. So all of this part of the instance is the same, so it's quite easy to match. But they also explored when you try to make it a little bit harder. The first variation that they tried is no lemma. No lemma is when you don't have a lexical match between the question and the needle. So in this case, which character has been to Helsinki, and the needle that is inserted in the context is actually Yuk lives next to the Kiasma Museum. And Kiasma Museum is located in Helsinki, so the LLM could deduce that Yuki is the character that has been to Helsinki. And also, when you have a clear match between the question and the needle, they made the problem a little bit harder by inserting some distractors in the context. In this case here, the needle is the best writing advice I got from my college classmate was to write every week. And the distractor is, I think that the best writing tip I received from my college professor was to write every day. So it's a different information. It's not responding exactly the question, but it still correlates quite well with the question. So it still might mislead the model to think that the distractor is the right answer. Regarding the experimentation, they have built different needles, so we could understand how the needle and the question affect the final result. And for each needle and question, they created embeddings using text embedding tree small, text embedding 3 large, Gina embedding v3, Voyage 3 large, and all mini LM L6 v2. And then they created an average, and they measured the similarity between the needle and the question. And then you have needle and questions that are similar and others that are kind of dissimilar, so they are most likely to make the LLM make a mistake. They also assessed the impact of distractors in the process. They assessed it without any distractor, with a single distractor, and with multiple distractors. And regarding the experimentation, they also tried with 8 input lengths, so varying the context size, and also 11 needle positions. So if the needle is positioned in the beginning, in the middle, or in the end of the prompt. And then they start discussing here regarding the experiment, how they did that. First off, they split the document into chunks. They generated the embedding for each chunk, reduced the dimensionality using UMap. And why they did that? They did that because if you have many dimensions in your problem and you start to measure distance, all the instances will have the same distance. This is a thing that can make difficult to deal with a higher number of dimensions. Then UMap is the guy to solve that problem, reduce, so we can better measure distance. Because the next step is to apply a clustering algorithm, and clustering algorithms are mainly built upon the distances. We want to measure distances between the instances, so we can group the ones that are similar, then the distance is lower, compared to others that the distance is high, then they should be in a different cluster. HDB scan is our algorithm to do that. Then they collected 20 representative chunks from the largest cluster using a method called maximum marginal relevance. This method is basically a way to properly extract a few samples from the cluster, because it tries to get the samples that are most different, so you can have like an idea of the whole cluster instead of just picking some examples that might be quite close and not being representative to the overall cluster. And then they analyze to see whether the needle, if we have any kind of leakage in the process, as well as defining the theme and the style that each cluster has. And then they are explaining here the process to write the needles. Here the results, basically they split it between 3 groups: the LLMs with high performance, the medium performance, and low performance, and also based on the quantity of tokens that they can receive. And then we have all of these three charts here, but essentially they are presenting the same information, which is, we have here in blue the needle and question that are quite similar, and the ones with low similarity is the orange line here. And essentially what happens is that when you increase the input length, so the context, the performance of the model start to drop significantly, and this happens for every configuration here. And they also assessed the impact of the distractors. So first they ran an experiment using only the needle, adding a single distractor, and adding 4 distractors. So here we have the results regarding the distractors. So in blue we have the results when we have no distractor added, 1 distractor as yellow, and orange is for distractors. The results are essentially the same, mainly the ones with distractors. But when we have no distractors, we can still handle a high input length. Then the performance still holds when you increase the context here. And I think that's it. They talk a little bit more about each of the distractors here. They also analyze the failures and how each of the distractors are impacting the response. And then we have here the performance segmented by the haystack and the needle. So we have the archive and PGSA needle and using a haystack context. And also they analyze a little bit when you shuffle the data set or if you keep the same logical rationale going. And it turns out that when you shuffle the data set, the performance is better. So the model can get easier the information that you want. And I think that's it for this problem. Now let's jump into the implementation that I made. Okay, now I'm here in the pie chart. Now we are going to talk a little bit about the code. We have here basically 4 scripts. The first one that I'm going to discuss is cluster representatives. It's partially the same as they used in that article. We have the data. I decided to go with some manuscripts from H.P. Lovecraft. It's a famous writer. And we have the stories here: At the Mountains of Madness, Call of Cthulhu, and The Color Out of Space. And this is the main function, I would say. It's the function that contains the same protocol as presented in the paper. So first they start by reducing the dimensionality. As I explained before, this is important so we can trust the distances and then properly use a clustering algorithm. Here I'm generating the clusters. I decided to go with a different algorithm. Instead of ADB scan, I'm using here k-means. ADB scan was returning a single cluster with most of the instances there. And for me, it was better if we could have multiple clusters that they were more correlated with themselves. Then I decided to go with k-means. And to decide the number of clusters, I decided to go with an locator. Let me open the chart. So here in the knee plot, you can see the inertia. Inertia is the error of the cluster. So for each cluster, we generate the centroid and we measure the distance against all the instances. And inertia is basically this distance summed. And we can see that it starts decreasing slowly from this point onwards, and then it means that this is a good point to cut and get this number of clusters. So in this case specifically, it was 6, the number that we decided to use. So regarding the MMR, the maximum marginal relevance, this is a method responsible for sampling instances from a specific cluster. And this is the implementation. I'm not going to discuss it in details. This function here is responsible for plotting the coverage. And by coverage, I mean I want to understand from which story the instances from a specific cluster came from. And then we have here a different plot. Let me show you. This is the largest cluster that we have. We have here 3 charts. Each chart represents a story from Lovecraft. And in the y-axis, we have the density. The density it's like a fancy histogram. We have a kernel, which is like a window that go through the whole histogram and start measuring which points have the highest number of instances. So we can see that from the color out of space, we have instances from the whole story. At the Mountains of Madness, we have specifically from the end, and Call of Cthulhu the real presence is from the beginning. This formed the second cluster that we generated. And then here we generate all the clusters. So we generate the clusters here, and then we get the largest two clusters and print the phrases. So let's run here so we can have an idea. I'm using here the MMR to sample some instances, and here we have the results. So these are the phrases contained in the second cluster. Nahum and Ami, they came from the color out of space, but yeah, basically that's it. So we are going to now start analyzing the needle. So this is a script that I use to evaluate the needles, so we can see whether we already have something related in the manuscripts. And so here we have the needle and the question that I decided to use for this experiment. The question is, what was the name of the book hidden beneath the gnarled oak in the blighted landscape? Describe it in the text. The first needle, the one which is a little bit simpler, is the book hidden beneath the gnarled oak in the blighted landscape was titled Al-Hazred Codex. And the second phrase, which is a little bit harder, is amidst the blighted landscape, a singular book lay hidden beneath the roots of the gnarled oak, inscribed with the name Hazred Codex in faded gilt. And then we get each of these phrases and we measure against the data set, so we can see whether we have any kind of related some phrases. And here we can see, I'm not going to check all the phrases here, of course, but I manually saw some of these phrases, and turns out that we don't have any kind of leakage in the needle or something like that. Finally, the script that actually run the experiment is here. We have the needle, so I'm going to use here as example the one that is a little bit easier, and we added some distractors here. The distractors try to change a little bit the phrase. So here is the scroll, not the book. Here we have cursed forest instead of blighted landscape, a tome, a map in a desolate wasteland, a chest, shadowy valley, a stone tablet. Here we have the same phrase, but it's saying that was written by Vosov. So it's not the title of the book, it's who wrote that book. Here we have the blighted hills, a journal, and so on. And then we have some other variances in the phrase here. And then we have some other functions here, but the main thing here is in the bottom, where we have the number of tokens that we're going to use, the number of distractors as well. And then we generate all the possibilities, and we are saving after running the results. Specifically, the model that I was running is 04 mini, and then we iterate through this function specifically, which is query LLM. First, we generate the context here, and then we call query LLM, which receives the context, the question, and the model, and it queries the LLM. And then we have here, we save the results. I just run for this alternatives here. So this steps in the context, this number of distractors, and the positions as well. 5 positions in the context. And the script responsible for analyzing the results is this one. We have here all the charts being generated, and if we check I decided to plot a few, and here we have a few charts. The first thing which is important to mention is that I'm using accuracy here, which is different than the metric that they use in the paper. They are using Liechtenstein distance, which is a distance between the tokens. And I'm using accuracy based on the name of the book. So I'm checking whether the name of the book is present in the answer. And we have two charts to present. So I'm going to discuss first this set of charts, which is when we have the logical context. I'm using only the at Mountains of Madness to build the context and then get the result. And after we are going to see what happens if we use the cluster 2 sentences to build the context. And turns out that the result is slightly different, so we're going to discuss it later. But jumping into this chart, we can see that the accuracy start dropping when we add more distractors. 04 mini, I'm comparing here GPT 3.5 Turbo with 04 mini, and we can see that 04 mini is way better than 3.5. Here we have the accuracy by needle position. Needle position is basically where the needle was inserted. So here 0 means it was inserted in the beginning and in the end. And turns out that both of these models are paying more attention to the beginning of the prompt. This is something that is different than the paper stated. They said that we didn't have any kind of correlation with the position of the node, but I saw that we do have for both of these models, we do have, and they are paying more attention to the beginning of the context. And here we have the same chart as they presented. We have the number of tokens in a log scale and the accuracy. Here 04 mini have like a perfect performance with a lower context, but after increasing the context, the performance starts to drop. GPT 3.5 have a lower performance, but we can see that the performance is dropping considerably. Here we have overall accuracy per model with GPT 3.5 and 04 mini. Here we have a heat map, which we have in the y-axis the number of tokens and the needle position. We can see that when we have a lower context, the model pay attention to the whole context, and then when we start to increase the context, we see that the performance start to drop, mainly in the middle / the end of the context. So the model still can pay attention here in the beginning. Now let's talk a little bit about the experiment when we have the context shuffled. Here we can see when the number of distractors increase, we have worsening performance. This experiment I ran with a few more models, GPT 3.5, 04 mini, GPT 4.1, and Gemini 2.5 Flash. Regarding the accuracy by needle position, in this case specifically, we don't have any kind of signal that the position matters. I mean, the 3.5 Turbo still matters, but as for some others, it's a little bit soft, so it's not really clear. Regarding the accuracy by number of tokens, in this case specifically, we still have a drop in performance, but is a little bit lighter, and that's expected because in the original paper, when we shuffle the context, the performance get better. So here we have a better performance as well. This is going in the same line as they stated in the paper. The overall accuracy per model, so GPT 4.1 and 04 mini were the best for this experimentation. Gemini 2.5 Flash performed a little bit worse, and GPT 3.5, which is a little bit outdated nowadays, the performance is way worse. For the heat map, we can still see that the accuracy is a little bit better when we have lower context. Also, when we have higher context, the first space, the first segment, performs better, but it's not really clear in this chart. So as the other one, as this one here, this one we can clearly see that we have a darker region here. In this case, it's a little bit more shaded. And here we have the heat map only for the 04 mini model. We can see that the performance is way better in this first segment, the top left triangle, while in the lower right triangle the performance is worse. But the same thing doesn't apply to GPT 4.1, for instance. And I think that's it regarding the results that I got. Now let's see the script. The algorithm responsible for generating all of this chart is this one. We load the results, plot accuracy per model, accuracy by tokens, heat maps, and accuracy by distractors, position, and so on, all the charts that I just presented. And thank you so much. I think that's it. The code is present in the description. Please feel free to use if you want. And I will add also the chart and so on in the repository, so you can check the results. And see you in the next one.